Hi boys and girls, this is lecture 7.7, Area of a Region Between Two Curves, Part 2. In this lecture, we're going to discuss integration as an accumulation process. The integration formula for the area between two curves was developed by using a rectangle as the representative element. As we continue, we'll determine an appropriate element based on known pre-calculus formulas to construct in order to calculate the area of the specified region. Then, each integration formula will then be obtained by summing or accumulating these representative elements. This means taking a known pre-calculus formula and then developing a representative element, which will then generate the new integration formula. For example, the area formula was previously developed as follows. We had the area of a rectangle, which was height times width. Applying this to our curve, we knew that the height of the representative rectangle was the difference between the two function curves. The width was the change on the x-axis, delta x. And of course, this generated the integration formula, the integral from a to b of f of x minus g of x dx. In this example, we're going to understand how integration works as an accumulation process. Find the area of the region bounded by the graph of y equals 4 minus x squared and the x-axis. Along the way, we'll describe the accumulation process. We have the integral negative 2 to 2 of 4 minus x squared dx, and as we know, that will calculate the area between this curve and the x-axis from negative 2 to 2. So let's find that integral. We're going to have 4x minus 1/3 x cubed from negative 2 to 2. And if we plug in these endpoints of integration, we'll see that the result is 32 over 3. That is the entire area underneath that curve from negative 2 to 2. But what if we had changed this integral a little bit and said negative 2 to x of 4 minus x squared dx? Of course, our indefinite integral is the same, 4x minus 1/3 x cubed from negative 2 to some x value that we specify. For example, if the upper endpoint of integration was negative 2, you can see that no area would have been accumulated between negative 2 and 2, and the value of that definite integral would be 0. What if we had let the upper endpoint of integration be negative 1? Then we would be looking at the area from negative 2 to negative 1. If we let the upper endpoint of integration be 0, we would have taken the area from negative 2 all the way to 0. If we had let the upper endpoint of integration be 1, then we would have accumulated area all the way to 1. And of course, when the upper endpoint of integration is 2, that's the entire area under the curve. Essentially, what you see is this representative rectangle that we use, which is accumulating area, is sliding along, adding area as it goes, depending on what the upper endpoint of integration is. Let's apply this principle in our next example. Find the accumulation function f, then evaluate f at each value of the independent variable given. F of x equals the integral from 0 to x of 1/2 t squared plus 2 dt. That's this function curve. Once we find the indefinite integral, we're going to evaluate it at 0, 4, and 6, calculating the accumulated area along the way. So let's integrate our function. F of x will be 1/6 t cubed plus 2t, and the endpoints of integration from 0 to x. So the value of this function will depend on the upper endpoint of integration. This means that f of 0 will be 1/6 t cubed plus 2t from 0 to 0. Now, as we can see by using my representative rectangle here, no area is accumulated if the lower endpoint of integration is 0 and the upper endpoint of integration is 0. So we know that the value of this integral has to be 0. The value of f of 4 will be 1/6 t cubed plus 2t from 0 to 4. If we plug these endpoints of integration in for t, we'll see that the value is 56 over 3. Now that means that as we move our little representative rectangle over to 4, at this point then, we have accumulated that much area, 56 over 3. Then the value of f of 6 will be 1/6 t cubed plus 2t from 0 to 6, which is an area of 48. So once again, if we move our representative rectangle over to 6, we have now accumulated this much area, giving us a total of 48 for that region. If we're integrating a rate function which determines the rate of change of a quantity over time, then the area accumulated under the curve represents the value of the accumulated change of that quantity. So let's do an example where we see the integral used to evaluate the accumulated change of a quantity. A cup of coffee is 90 degrees centigrade when t equals 0. If the coffee's temperature is changing at a rate given in degrees centigrade per minute by R of t equals -7 e to the -0.1 t, where t is in minutes, estimate to one decimal place the coffee's temperature when t equals 10. This rate function is determining how the temperature of the coffee is changing over time. So integrating this rate will give us the value of the total accumulated change in temperature over a certain period of time. So let's find the integral. We'll have the endpoints of integration from 0 to 10. And of course, our rate function is the integrand, -7e to the -0.1 t dt. I'll take the -7 outside the integral, and since my u here is -0.1 t, then my du will be -0.1. I'll need to insert that in the integrand and divide the constant outside by -0.1. This means that I'll have 70 e to the -0.1 t from 0 to 10. Inserting the upper endpoint of integration gives me 70 e to the -0.1 times 10, and then inserting the lower endpoint of integration, 70 e to the -0.1 times 0. This becomes 70 e to the -1 minus 70, which is approximately equal to -44.2 degrees centigrade. This represents the accumulated drop in temperature of the coffee from 90 degrees at t equals 0 to the temperature it is now. Since we started at 90 degrees, subtracting 44.2 gives us a final temperature of 45.8 degrees centigrade. That's it for today's lecture. Pie, where irrational and delicious come together. God bless you, boys and girls.